Hello everyone, welcome to this video. In this video we shall be discussing about differentiation property with respect to frequency. In the last video we have talked about this differentiation property with respect to time. So let's now discuss this with respect to frequency. So that means we are having differentiation in the frequency domain. So the conditions that are required here are that the given function f of t that should be piecewise continuous on every interval minus L to L, where L is some random number, and we say t to the power n into f of t, this should be absolutely convergent. Then this is our property that the Fourier transform of t to the power n f of t is equal to iota raised to power n capital F nth derivative omega. Or basically you can say this is the more precise result describing this property, differentiation property with respect to frequency. How? Because when you take the inverse Fourier transform of the derivative of the function, you obtain minus iota raised to power n t to the power n f of t. If you remember, when you apply the Fourier transform, in the previous video we have discussed this result. If you apply the Fourier transform onto the derivative of some function, so then you obtain iota omega raised to power n capital F of omega, where this capital F of omega was what? It was the Fourier transform of the function f of t, right? So that means whenever you have the derivative here, you multiply by iota to the power n. But in this case, when you have the derivative in the frequency domain, so you multiply by t in the time domain. So you can relate this accordingly. Or in conversely, when you wanted to talk about this forward Fourier transform, so you can say that when you multiply by t, you have the derivative in the frequency domain. So in order to justify this property, let us see what are the results when you have the first order derivative and the second order derivatives. So when you have the first order derivative, so suppose the Fourier transform of the function f of t is capital F of omega, so we can write down the definition of Fourier transform of f of t, which is this one. So accordingly, our first derivative becomes equal to d by d omega of capital F of omega. So we can apply this definition here, and then we can interchange the limits of integration and this derivative. Why? Because this integration is performed with respect to t and the derivative here is with respect to omega. So accordingly we can interchange them, and now because we are to take the derivative with respect to omega, so we only will perform the derivative of this particular term. So here when you take the derivative of this term, so accordingly the coefficients iota and t, they will come as multiplication in the multiplication, and all the other terms, they are as such, right? So that means you have minus iota into t f t to the power minus iota omega t. Now if you look at the definition of this Fourier transform of some function f of t, so accordingly whatever is the function here, that forms the Fourier transform of the function f of t. In our case we have t f of t here, so that means you can write this to be the Fourier transform of t into f of t, right? So we have f dash omega is equal to minus iota f of the Fourier transform of t into f of t. So let's match the results here. So when you have the power 1 here, so that means we are writing which result? This result. So when you have the power 1 here, the first derivative, so it would be equal to minus 1 iota raised to power 1 t to the power 1 f of t. So that is the same result that we obtained here. Okay, so now let us move on to the second order derivative. For that we are differentiating this f dash omega again, so that we have f double dash omega, so it would be minus iota as such, taking the derivative of this term. So the derivative of this term, I am again writing this integral form of this particular function. So again here the integration is performed with respect to t, and we are performing the differentiation with respect to omega. So they are independent of each other, so we could interchange the integration and derivative. So we can shift this derivative inside this integration over here. Now all these terms, they are depending on t. However, this term depends on omega. So that means we'll differentiate this term here. So when you differentiate this term, you have this as such, and the coefficient of omega as minus iota t here as such. All the other things, they will be coming as such. So that means you have minus iota raised to power 2, so iota square, and you have t into f of t, so that means t square ft, function of t. So now if you look at this definition, what is this definition? This is the Fourier transform of this particular function, t square f of t. So this is what we have here, right? So this is your second derivative, and according to the definition for the nth derivative, we have minus iota raised to power 2, that is simply minus, and then we have t square f of t. Okay, so now let me discuss a question with you. They are asking, find the inverse Fourier transform of this particular function. So when we will calculate the inverse, how we can approach this question? The first thing, here you can see we have this term omega and e to the power minus omega square. Now as such, they performing the inverse Fourier transform of this particular function is quite difficult. So what one can do is, they can make an observation that if you differentiate this function, you have this function as such, and then according to chain rule, you will have 2 into omega minus 2 omega by 8, right? So accordingly, you have this omega here. So all in all, you can write whole of this thing as the derivative of some quantity. So that is what we are doing here. So when you perform the derivative of this term, so you will end up by this term. So what is this? This is by 4. So you can replace omega into e to the power minus omega square by 8 as equal to minus 4 into d by d omega of this whole thing, right? So I have separated out this term, and I am substituting the value of this as this over here in the given function. So that means your function now becomes minus pi as such, 4 root 2 pi as such, and then e to the power minus omega square by 8 in place of all of this. So in place of this term, I am now substituting this term, right? So it become this. So from here you see this 4 and 4 cancels out, so we have this thing. So when you apply the Fourier inverse onto the derivative of some function, now what is this? This is some f of omega. So you have the first derivative of this f of omega. So when you perform this first derivative here according to the formula, when n is equal to 1, your formula simply reduces to Fourier inverse of the first derivative of omega, that is equal to minus iota raised to power 1 t to the power 1 f of t, right? So you can now write in place of this as minus iota raised to power 1 t to the power 1 f of t. So we have to compute the inverse Fourier transform of this, because initially what was your f of omega? It was the Fourier transform of f of t. So therefore this implies what will be your f of t? It would be the Fourier inverse of capital F of omega. So we have to perform the inverse Fourier transform of this particular function. So now all these quantities, they are as such, minus minus becomes plus, this iota and iota cancels, so we have square root of pi by square root of 2 into t f of t. Now what is this f of t? So for that we have to take the Fourier inverse of this function. So when you perform the Fourier inverse of this function, so I have done it over here. So this was your function. Now its Fourier inverse would be equal to, now according to this formula you can verify that you already know that Fourier transform of e to the power minus a t square, that is equal to square root pi by square root a e to the power minus omega square by 4a. So according to this, when you compare this quantity with this quantity, you can see that your 4a is equal to 8, so that means a is equal to 2 here. So if a is equal to 2 here, so this would be, in place of this we have e to the power minus 2t square, right? So that means this thing is nothing but the Fourier inverse of this particular function. So in other words, I can write this as, I could shift these two terms here on the left hand side, so that I have square root a divided by square root pi into the Fourier transform of e to the power minus 2t square. Our a is also 2, so we have square root 2 here, right? This is equal to e to the power minus omega square by 8, right? So using this result, so from here I can conclude that the inverse Fourier transform of this thing is equal to this function. So utilizing this value over here in the expression, so you see we are left only with this term, which is t into e to the power minus 2t square. So this is the inverse Fourier transform of the given typical function, right, which we have solved this by making use of this differentiation property. Well, that is it for this video. I hope you understood the concepts well. Thank you for watching.